you all read the section in the book? I know you did. I know you did. Trying to get a giant clock on the screen over here so I can see it. Okay, so today we're doing section 1.6. Sets of solutions. Is that 1.7?
Or 1.5.
1. Right. You are correct, sir. Sets of solutions. And these are sets of solutions to the equation, the matrix equation AX equals 3. A big part of this class, big part of any class that deals with matrices has to do with solving this equation. In practice, this is what people usually want to do, is solve these sets of equations. There are other things as well, but okay. So in order to talk about this, well, what do I mean by a set of solutions? I mean a set of vectors that I can put here in place of x, given matrix A, and let's say this is an M by N. Let me try again. Given an M by N matrix A, so that is a matrix with M rows and N columns. So given this matrix A and vector let's see, we want an M by 1 matrix, which is also an M dimensional column vector, which we call B. We want all N by 1 vectors X such that AX equals B. So we want to collect all of the solutions together and say this is all of them. We call that a set of solutions. And we'll see that this set, the set of all solutions, has a special structure. There's a special structure. And to see this, we will we'll look at special equations first, and put it all together. Okay, so remember that this AX equals B is the same thing as saying, if we say A is equal to the columns A1, A2, up to how many columns we have? N, AN, and X is equal to this column vector, X1, X2. Now this has to have as many entries as this has columns, right? That was our idea for linear combination. So this goes down to Xn. And B, we will also be writing as a column vector. This will be B1, B2, Bm. So this thing will have the same height as these because it's going to be a linear combination of these columns. So we're going to mix these columns together. X is going to give us the proportions, and B is going to be a combination of those, so it's going to have the same height, and that height is M. So this is the same thing as saying X1, A1 plus X2, A2 plus Xn, AN equals B. So this is rewriting this equation in terms of vectors. And then another way that we can write A is we can write out the entries of it. And we had a special naming convention for each of the entries. This was A11, this was A12, and I got A N 1N. And the first number indicates, the first index indicates the row, and the second indicates the column. And so we have A21, A22, this goes down to AM1, and this goes all the way over to AMN, and I'll put dot, dot, dot in all the different directions. You know how to fill this in the rest of the way. And so what we're saying is that we have this system of equations that comes from this. We have A11 x1, and we do this multiplication. This x gets multiplied by the first column vector, so the top equation will be A11 times x1 plus A12 times x2, all the way up to A1n xn equals B1, and then A21 x1 plus A22 x2. It's really good to be able to mentally translate between these different ways of writing this same equation. This will be A2n xn equals B2. So that'll be the second entry in B. And the system of equations continues until we get down to A1 x1 plus A2 x2 plus dot plus A xn equals B M. That's right. This will be the bottom entry. So this continues all the way down until we have all of the entries. And if you looked at the rest of the section, we didn't get to talk about the whole section last time. This is basically how we do matrix vector multiplication. This is what we think of as matrix vector multiplication. We're taking this column vector, and then we kind of set it along this right here. So it's A11, A12, A1n. Each of those is multiplied by x1, x2, up to xn, and then added together. And this is the way we do this multiplication. Kind of take this column, set it along here, do the linear combination. Take the column, set it along here, do the linear combination. I really recommend that you practice that so that you get quick at it. All right. So when we have another way to look at this is the augmented matrix AB, which if we take this system of equations and we transfer it back to the thing we did on the first day that we actually talked about math, we turn it into an augmented matrix, and then we can do things like row reduction. Are there any questions at this point? Everything clear? Okay, good. Trying to gauge if I'm going too quickly or too slowly. I will attempt to adjust my speed, and make no promises. So in this case, we had thought of this as this was our first introduction to dealing with the matrix, was the augmented matrix. Now we're going to deal just with the coefficients. We call this the coefficient matrix. And these are A1, A2, AN. Typically when I say a matrix, this is what I'm going to refer to for the majority of this class. If you need to do that again, I ask that you step out in the hall, okay? I just want to be very clear, you cannot take your mask off in this class. If you need to take it off, you need to step outside. Okay, so now the point of view is that we're thinking of this as an object on its own, right? And it's as if we had the equation mx equals b, where m was just some real number and b was just some real number. Now we're dealing with them in terms of this larger world of things that we can deal with. This A is a matrix, the x is a vector, we're multiplying a vector by a matrix to get a vector. So the first type of equation that I would want to look at, well, this is just a special type of equation. One that we said earlier, this one always has a solution. Let me write this. What can I put on the right-hand side so this will always have a solution? 0, yeah, exactly. And what is the solution that this always has? 0. Yeah, what would it be if it was just mx equals b, right? Mx equals 0, x equals 0 would always work there.
So A is a 0 vector?
No, A is a matrix. Remember this convention that we're using, that A represents, capital letters represent matrices. I'm always going to stick to that.
I was thinking of I guess vectors, 0 vectors when you just have one column.
It would, yeah, exactly.
Okay.
Now you may mean the 0 matrix, right? A matrix that has all zeros in it.
That's what I was thinking of, just A is all zeros.
Let's take a look at this example, actually. This might be a good example to look at. Let's have a 2 by 2 0 matrix. This is a matrix with just zeros in it. If I multiply this by 1, 2, okay, so I'm writing down now the multiplication. I'm realizing I haven't done any examples like this, so maybe this is good. I take this column, and I don't remember who said this originally, but we talked about a product between vectors. We can think of this as that kind of product. This would be, doing this linear combination is the same thing as doing the dot product in Calc 3. So it's 0 times 1 plus 0 times 2 is the top entry, and then I take this and I lay it like that, and I get 0 times 1 plus 0 times 2 again, and I get 0, 0. If we had, if it were the case that we could multiply something by this and get 0, let's call it capital Z. So if Zx equals 0, and we say x is not 0, we would conclude, at least in the old case, in just the real number case, we would conclude m has to be 0, right?